Welcome back. We have with us here today Bill Szafranski from Lynker Technologies. Bill's a water resource scientist, and he's going to talk to us here about his risk assessment. So, Bill, I'll hand it off to you.
All right, great. Thanks, Paul. I'm going to share my screen here and kick off this presentation. All right, that's looking good, right, Paul?
We're seeing the presenter view.
Oh, interesting. Try that one more time. How about that?
Looks great.
Great. All right. Sorry about that. All right. Hey, everybody. I'm Bill Szafranski. Work at Lynker Technologies in Boulder. So today I'll be talking about the Colorado Face Hazards Project. So we're quantifying Colorado's current and future wildfire risk. So this is the summary of, like I said, Face Hazards, the Future Avoided Cost Explorer. So first of all, I just want to give a shout out to the project sponsors. So this is a mini agency collaboration, really supported by FEMA funding and Colorado Water Conservation Board, as well as the Division of Homeland Security and Emergency Management, among others. Additionally, we had a great team that was working on this project. So here I'm just kind of calling out some of our project collaborators that were a part of the Lynker team. All right, so to kick this off, here's a brief outline of what I'll be talking about today. I'll give a quick background on the project, then we'll talk about the project as a whole, and then we'll dive into the wildfire components. So we'll talk about wildfire building damages, and we'll talk about wildfire suppression costs. All right, so a little bit on this background. This project is really a continuation of Colorado's hazard mitigation plan updates. So they had recently done that update, and then they were looking for that next phase where they wanted to understand future vulnerabilities. And from that mitigation plan work, they really honed in on 3 specific hazards: flood, drought, and wildfire. So those are the components that became a part of this project. Additionally, they really also wanted to really bring out a visualization and user-friendly element. So that's also a part of the project. So diving into kind of our project steering questions, I've kind of listed out here 5 questions that were a part of that. The first one being really important: what is Colorado's current and future risk given flood, droughts, and wildfires? So that's really the, kind of the core of the project. Additional considerations were what's going to happen given future population growth, what's going to happen to the impacts given climate change, how can we understand these economic impacts to Colorado's economy, and what are some possible resilient actions that we can take to then reduce that risk in the future. All right, so what are we all talking about here? Ultimately, we came together and developed this Face Hazards portal. So that's kind of what I'm showing you here right now. This is the project landing page on the Colorado Water Conservation Board website. And we'll come back to this again at the end of the presentation today. But I wanted to give you a brief introduction, show you what it's all about. It's meant to be a user-friendly website. You can go click on it. You can explore results. It's interactive, it's user-friendly, and it should be pretty intuitive as well. All right, so let's dive into the project as a whole. So like I said, we're analyzing 3 hazards, so flood, drought, and wildfire. And we're also analyzing different vulnerabilities as a part of those hazards. So for flood, we looked at buildings and bridge damages. For drought, we looked at rafting, boating, skiing, cattle, crop damages. And for wildfire, which of course we're going to be talking about today, we looked at suppression costs and building damages. All right, so a big part of this project is that we're looking at today's economy, 2019 dollars, and tomorrow's climate and population. So with that in mind, we are comparing current climate conditions to those future climate conditions. And so we're looking at conditions around 2050. We analyzed 2 scenarios. This is, we call them moderate, kind of a middle of the road climate projection, and then more severe, which can be thought of as, more severe climate scenario. Not the most extreme, but more severe than middle of the road. Additionally, we looked at 3 population scenarios. So we have our current population projection there at about 5.5 million. And then we used the state's population projections for 2050, looking at low growth, medium growth, and high growth. All right, so in addition to getting population magnitudes, so again, I'm showing those magnitudes of statewide population on that bar chart on the left. We also needed to be able to understand and project spatially where the population was going to exist and grow in Colorado. So to do that, we used a product from the EPA called the Integrated Climate and Land Use Scenarios. That's ICLUS version 2. And so what that allowed us to do was track changes in land use given population growth and climate models done by the EPA. So what you can see on this GIF here on the right side is Boulder County, projected changes in Boulder County given these future scenarios. So those oranges are changing to pink, which is representing higher population density land use change. So how do we apply this? What we needed to do, of course, was then combine population growth with dollars of assets, right? So for wildfire, we're interested in suppression and building costs. So we use the HAZIS census block building replacement value, and we combine that with those ICLUS population changes. So we use the ICLUS land aerial coverage, combine that with HAZIS, and then we're able to come up with this area weighted replacement cost. So as you can see in this figure here, these orange pixels have about $2,500 per pixel or per model grid cell, whereas these red values have about $58,000 of value per pixel. So as we have more population, we have more dollars of assets, and that's kind of the way that that modeling works. Then we need to also project this forward. So we take that current value, that replacement cost per pixel per land use type, and then we combine that with these future changes from ICLUS population growth, and we're able to come up with a future replacement cost. So that's how we then project those costs into the future without actually knowing, precisely what's going to happen, of course. So in this figure, we're showing that change in dollars. As population increases, those dollars of assets also increase. All right, so now let's dive into the building damages. So on this figure, we're showing a conceptual model for our modeling framework. We'll talk about each of these components in a little bit more detail. So burn probability and flame length are a critical part of this analysis, and those come from a wildfire behavior model. The building values we just talked about a little bit, those came from HAZIS census data sets. Those population projections were a combination of the Colorado state's projections as well as the ICLUS spatial projections. And those climate scenarios, we'll talk a little bit more in the future here, those are also Colorado focused scenarios specific for Colorado. So we bring all these together and then we're able to kind of calculate those building damages. So here's another mock-up of how we're thinking about wildfire risk. So this figure is actually taken from the Colorado Wildfire Risk Assessment Update 2018. We're combining 2 parts, hazard and vulnerability, together to calculate wildfire risk. So that those hazard elements come from that wildfire behavior model. So we have probability and wildfire intensity. And those vulnerability elements really come from our ICLUS and HAZIS data sets, where we have that location, that spatial arrangement of assets, and that susceptibility, which we'll talk a little bit more later. All right, so here's a slide kind of giving an overview of this wildfire behavior model. So this image on the right is showing a snapshot from what is now called the Colorado Forest Atlas, where you can go follow that URL and check out your wildfire risk on kind of a 1 to 5, 1 to 10 scale for any part of Colorado. So the inputs into this model are your climatic data, such as air temperature, relative humidity, and wind. And then the topographic data, such as slope, aspect, elevation. And then those vegetation fuels data sets are also a major input to the model. And model outputs that we're getting are going to be the annual burn probability and those flame length probabilities. And we'll talk about both of those more right now. So the annual burn probability is really that probability of a model grid cell igniting in a given year. So this model that we use is a 30-meter gridded model for Colorado. So these burn probabilities are really driven by historical ignition data, as well as running over 2 million simulations of burn ignitions. And the end result of that is this annual burn probability. Again, that likelihood of having a fire burn in any given model cell. So this map on the right, those darker colors, again, we're showing Boulder County. Those darker colors are more likely, they have a higher burn probability. Those lighter yellows have a lower burn probability. All right, so that second element that comes out of the model is the flame length. And flame length is actually binned according to these buckets. So we have about 0 to 2 feet, 2 to 4 feet, 4 to 6, 6 to 8, 8 to 12, and 12 plus. And so I'm showing those flame length probabilities in this map on the right. So we can see that if we look at, again, these are showing Boulder County, we look at that bottom right map, we can see that those darker red colors are representing higher probability of getting those greater than 12-foot flame lengths in the foothills of Boulder County. And we can see that we kind of have lighter colors in a lot of the other flame length bins. So if we combine all those probabilities together for all those flame length buckets, we can instead kind of look at a conditional or an average flame length map. And so that's now what I'm showing here for Boulder County. Again, we can see that the most probable, the most likely flame length for the foothills of Boulder are those higher flame lengths greater than 12 feet. Whereas in the plains, the eastern half of Boulder County, we can see that we're more likely to get those lower flame lengths, less than 8 feet, less than 4 feet, less than 6 feet. All right, so another critical element is to relate then wildfire severity, that flame length, to damage. And so we do that using a response function. And so we worked with a team of experts around Colorado to kind of figure out what the best values were to use for this. We also looked at some other examples of response functions that are available in the literature. So that column on the left, we're showing values from Scott et al., a US Forest Service paper. That middle column is showing values collected by a Spanish team. And that column on the right, we're showing the values used as a part of this face hazards project. So to kind of break this down a little bit more, in that 0 to 2 foot flame length bin, we assigned 0% damages to a building in that grid cell. Whereas flame lengths of 8 to 12 feet or 12 feet and greater got 100% damage if a if a fire burned in that grid cell. All right, so when we combine all these elements together, we can kind of look at that wildfire hazard component where we're combining burn probability there with the BP, flame length probability, and that flame length damage associated with those flame lengths. So in those yellow and orange shades, you can see, again, that probability of hazard increasing in those oranges and reds. And behind that, I've got set the building values so that those assets that are available, that are located in that area and can burn. And so when we combine those two data sets, we multiply those building damages times that wildfire hazard, we come up with our building damages. And so now that's what I'm showing here in this figure. We can see where we have a coincidence of more building assets and more wildfire hazard, we have more damages. And so those foothills of Boulder County have the darker orange and darker red colors that are portraying more building damages. All right, so let's talk a little bit now about how we progressed these wildfire damages into the future. So again, we looked at a couple climate change scenarios, and one of the things that we perturbed in our model was average monthly air temperature. So we used a series. These climate change scenarios came from the Colorado Water Plan, and so what we're looking at for this moderate climate change scenario is an increase of 3 degrees Fahrenheit in summer temperatures. And in that more severe climate change scenario, we're looking at an increase of 3.4 degrees Fahrenheit. So that was one adjustment we made to the wildfire behavior model. The second factor we used was live fuel moisture content. And so this fuel moisture is what quantifies that water content of your trees, grasses, and shrubs. So as that fuel moisture decreases, your vegetation becomes more drier and of course more flammable. So what we did there was we developed a relationship between a drought index called the Standard Precipitation Evapotranspiration Index and the live fuel moisture content. Then we modeled that drought index forward in time to 2050 conditions, and we were able to see how those fuel moisture contents then changed in the future conditions. So what we arrived at here is a 12% decrease in that moderate climate scenario and a 21% decrease in that more severe climate scenario. All right, so looking at our population scenarios, again, we talked about these a little bit already. We used ICLUS and HAZUS data sets. And as those population scenarios increased with more population, we've got more building assets available and therefore more potential for damages. And so that's kind of what we're showing here in this figure, is that as we have future population, we have additional exposure to assets and thus additional damages. All right, so to kind of summarize these wildfire results, one of the last steps we did was aggregate these model grid results to the county scale. So we summed up all those values within the county, produced results at the county level. Additionally, this wildfire risk is quantified as expected annual damages. And what that means really is that, we're not quantifying the actual damage from one wildfire event in one location. Instead, we're really using those probabilities, that annual burn probability, to get that average expected value over a longer period of time. So if we have 1% chance of burning, we multiply that by the assets in the grid cell, and that's how we arrive at kind of this average expected damage. And then finally, of course, like I've said before, we're looking at today's economy, tomorrow's climate. Everything's expressed in 2019 dollars. All right, so taking a look here at our countywide results for Colorado, I've got 3 images shown here in succession. Number 1 is showing current population, current climate. Number 2 is showing 2050 low population and moderate climate. And number 3 is showing 2050 high population and more severe climate. So number 2 and number 3 kind of bookend future damages in this scenario. And what we can see is that in those kind of, fire exposed counties, of course, those damages increase given these future scenarios of population growth and climate change. If we step a little bit further into detail, we can look at all of these scenarios and how they compare with one another at a statewide level. So our historical costs of building damages on annual, we calculate to be about 138 million. So that's reflected in this value that I've highlighted here of 1. So current population, current climate. If we then increase only our population scenarios, we can see that those costs then scale up as relative to current conditions. So low population growth gets us 1.6 times damage, and high population growth gets us to 1.9 times current damages. If we look at those climate change scenarios only, we can see that the moderate climate scenario gets us 1.6 times current value damages, and the more severe climate gets us 1.7 times current damages. So now when we combine climate change and population growth, we can see that those values, of course, increase with that compound effect. So that moderate climate, low population growth is about 2.1, whereas that more extreme scenario is about 2.9. So we can see that cost increase in 2050 bracketed about 2.1 to 2.9 times current costs. All right, so now let's step into the wildfire suppression costs. We also analyzed the suppression costs because, of course, they're an important element in the costs associated with wildfire in the state every year. So again, here we're showing a conceptual model of this framework that we used. For this, for the suppression cost analysis, we only use burn probability. We got that from that wildfire behavior model. In our building footprints we used in this case, and that came from this Microsoft building footprint data set. Our population scenarios are the same as they were in the building damages scenario. So those came from the Colorado Water Plan and ICLUS. And finally, we're also using the same climate change scenarios as we used for the building analysis. So one of the first parts we had to do for this project was compile historical suppression costs for Colorado. So here I've shown a snapshot of some of those costs that we aggregated for different wildfire events in Colorado. Secondly, we used the GeoMac wildfire burn perimeters to then get these burn areas to use in our analysis. And finally, like I said, we used the Microsoft building footprint data set to associate nearby buildings to nearby wildfire events. And what we were able to do is come up with a multiple linear regression analysis to then associate both wildfire burned area and number of nearby buildings in a 6-mile buffer to that cost of suppression. So you can see I've got the general form of that regression model there on the right. And so let's take a look at those results and kind of what they show. So this model we found actually explained a lot of the variance in this data set. So what we're looking at here in this plot now is we've got suppression costs in the y-axis increasing as you go up. We've got burned area increasing as you go right on the x-axis. And we also had the number of nearby buildings in that 6-mile buffer shown in those circles. So more buildings nearby is represented by a larger circle. So again, this is multiple linear regression analysis, and you can see that this did a pretty good job explaining a lot of our data. So the next step we had to do then was bias correct these results on a statewide level. So really the only available data was, as it's kind of shown here in this chart, from the Division of Fire Prevention and Control. So we used our historical statewide fire suppression costs, which we calculated to be about 18 million per year. So we then bias corrected each county's results using this factor here. So again, we then took this model and we projected it forward in time using these climate change scenarios and population scenarios. So as I mentioned before, these climate change scenarios are the same as we used in the building damage analysis. We had moderate and more severe climate. For these population growth scenarios, again, we're looking at low, medium, and high. And in this case, we had to associate these Microsoft building footprints with the ICLUS data set. So we associated an average number of buildings with a given ICLUS land use type. And so then as we projected those changes in ICLUS land use type forward, those associated building counts then increased relative with those increases in land use. All right, so we come back to this slide. Then we are able to then take those updated burn probability charts to reflect climate change and those updated Microsoft building footprints to represent population growth. We combine those into our model again, and we're able to project now future costs for wildfire suppression. So when we pull all this information together, we can again take a look at our results at that county level. And so that first image is showing, again, current conditions, current population, current climate change. And then that second image is showing 2050 low population growth and moderate climate. And then that third image is showing 2050 high population growth and more severe climate. So again, number 2 and number 3 kind of bookend potential increase in suppression costs going into the future. So again, if we then aggregate these results statewide, we can look at a relative change in suppression costs to current conditions. So again, those historical costs, on average, we calculate to be about 18 million a year. So that's represented by that value of 1 in that yellow box. So if we look at only increases in population growth, we can see that suppression costs are projected to increase by a factor of 1.4 to 1.9 relative to current conditions. If we look at only climate change, we can see that those suppression costs are projected to increase by a factor of 1.4 in both cases. And then if we combine population and climate change together, we can see that suppression costs in 2050 are projected to increase by a factor of about 1.9 to 2 in 2050. All right, so then to kind of summarize what we've talked about here in dollars for building damages and suppression costs, we're kind of showing the end results here in this chart. So those building damages are shown in the blue and the suppression costs are shown in the orange. So again, we've got current conditions on the left, we've got moderate climate and low growth 2050 in the middle, and more severe climate, high growth 2050 on the far right. And so those 2 right columns kind of, again, band that potential increase in damages in future 2050 conditions. So what we can see looking in dollars now is that those building damages are projected to increase from about 140 million to about 300 to 400 million in the future. Those suppression costs are projected to increase from about 18 million to about 30 to 40 million in the future. All right, so that brings us back to the Colorado Face Hazards landing page. So now I've added the URL here up on the website, screenshot, so you can hopefully navigate there yourself and check it out and take a look. And so here I've added up a little graphic showing how interactive this website is. So we really encourage everybody to take a look. You can go there, click around, explore the different hazard implications from flood, drought, wildfire. You can check out your county results. You can check out your regional results. You can explore these damages according to economic sectors. There's really a lot of interactive nature to this website. Additionally, I also wanted to talk about a few of the other elements that are available in this website. So for instance, we built a project overview to kind of summarize that, what we did for that project. We also built a series of case studies. So obviously this analysis was done at the county level and we're looking at Colorado as a whole. But of course, all of these incidents are really, they occur at the local scale. And so it's hard to kind of, cover the impacts as they happen at that local scale when we're looking at county and statewide results. So we built a few case studies here for flood, drought, and wildfire to kind of dive into those local impacts from these events. So for wildfire, we took a look at the Missionary Ridge Fire in Durango in 2002, and we kind of stepped through some of the same things I talked about in today's presentation. So we talked about changes in fuel moisture content, we talked about changes in air temperature, and we also talked about how those impacts then result in an increase in damages. All right, so just to wrap up here, just a few thoughts about what's next with this tool and where can we go. As I mentioned, this project is really statewide analysis done at the county level, and therefore a lot of our data inputs going into this are reflective of those kind of higher aggregated level inputs. So of course, results could always be improved by using more local, higher resolution data sets. Additionally, we're only looking at a few select sectors of Colorado's economy. We could also use this analysis to extend it and look at other vulnerable assets in the state. other economic sectors in the state that are impacted. And finally, we don't really touch on too much the development of adaptation scenarios. So what are the impacts of, having restrictions on WUI growth? And what are the impacts of, building hardening or defensible space? That stuff is a little bit harder to model at this coarse scale, but those are definitely considerations for, for future exploration. So with that, that's my presentation. So thanks everybody for your time and tuning in.
Hey, Bill, thanks for that presentation. Really fascinating stuff, and certainly shows a lot of the need for why we're all meeting here together. Couple of questions that were posted. One, would you be able to copy your website link into the live chat feature? I think some of the graphic was cut off on the top there.
No problem. Let me do that right now, actually.
Awesome. And then while you're on that, there was a question about was wind speed part of the flame length equation in the fire behavior calculations?
Yes, it was. So yeah, wind speed was definitely part of that wildfire behavior model, but wind speed was something that we did not adjust for future climate change. It's one of those variables that is really hard to know what's happening in the future. So of course we have really high confidence on what's happening in air temperature given climate change, but there's much more uncertainty about what's going to happen to wind speed. So we left those, when we were projecting into future scenarios, we left wind speeds as is.
Excellent. Do we have any other questions from folks out there in the audience?
And I just dropped that landing page there in the chat box.
Excellent. We'll give it a few here. We got about 10 more minutes in our session.
Sure.
And I am not seeing any more questions pop up here, but I'm sure Bill would be happy to hang around here and answer anything that you have. Bill's contact information is up there as well, so feel free to contact him directly. We'll also be posting the presentations so that you can go back through and take a look. Certainly encourage everybody to go to the webpage there and explore around on the tool. Again, I see a lot of really good value, especially when we're communicating messages to our decision makers and why we need to continue with the strong work that's going on. So tools like this, I think really provide some good scientific backup to the messages that we have. So.
Yeah, and I'll just jump in and just say that was definitely a major purpose of the project, is to show there's a lot of talk about climate change and its impacts, but we wanted to really quantify that in terms of dollars and understand that what's at risk going forward if we do nothing, right? So that's really a big part of this project, is just to try and kind of show some of those economic impacts in the future, if we just kind of let things move forward, business as usual.
Great. All right. Well, yeah, if you don't have anything else, Bill, I'll probably sign off here, but appreciate everybody jumping in and joining us. And Bill, great presentation. Thanks for your time.
Yep. Thanks, Paul. Thanks, everybody.